things will happen if you eat any of these samples. All right, so I'm the fun one here. The whole rest of the week has not been enjoyable. So we're going to talk a little bit about, so this is just a rivalry that happens between the chemists and the physicists when you work at a lab like this. So we're going to talk a little bit about some applications. So you heard Ryan Rogers talk yesterday about the fundamentals of ion cyclotron resonance that we do here in the ICR facility at the MagLab. We're going to talk a little bit about how we use that technique to solve real-world problems. So complex mixture analysis is the sweet spot for ion cyclotron resonance mass spectrometry. And so we're going to look at some of these are samples that are actual samples sent from users. And I'll talk about these and pass them around. Just like I tell my 5th graders, please don't take the tape off and open them up. So complex mixture analysis and what we call environmental petroleomics. So this is a schematic screenshot of something that happened in 2010 when the Deepwater Horizon oil spill happened in the Gulf of Mexico. So we're 18 miles from the coast in Tallahassee, so this is very much a local regional topic for us. So this is a picture that was collected while the actual well was still spewing oil, because what happened was they were unable to plug that well for 87 days. So oil was leaking into the Gulf of Mexico straight out of the reservoir 50 miles off the shore of Louisiana. And there is a sampling mechanism in this picture here. This is taken from our collaborators at Woods Hole Oceanographic Institute up off of the coast of Massachusetts and Cape Cod, where they had a sample holder that actually injected while the oil spew is what they're calling it. While it happened, they collected oil that was being released. And that is the only sample that is being reported by the NOAA and the US government as collected while the spill was happening. These are skim boats. One thing that happens when an oil spill happens is that they try and immediately contain the spill because oil floats on the surface of water. So they put out these booms. Usually they repurpose shrimpers in the area who are no longer able to fish to do this work for them. These are sand patties. They call these, they look like half-baked brownies, so they call them the half-baked brownies or sand patties. So when you split them open, there's still gooey oil in the middle, as well as some rock scrapings from oil that splashed on to the rocky jetties in the Gulf of Mexico. No, I never work this right. Okay, so here's where we're at. So you guys have seen all of this. You guys are sitting right here in the first floor. So I'll just make a comparison. This is where all the physicists are, and this is where all the chemists are. So we're like really far away. They have all the world's biggest magnets, and we have all the superconducting magnets down in this end of the building. So why do we care? So the bottom line is we're not running out of oil. We're running out of oil that's easy to get at and that we know how to refine. So all of the refinery strategies and all the refineries in Houston are based on what is called light sweet crude oil. So light refers to the viscosity and sweet refers to the amount of sulfur. So this is a light sweet crude oil. You can see it's very yellow. It's got a really low viscosity. And I'll just kind of pass that one around. We're running out of that's easy to get at. Where that is buried under 8,000 feet of water in the Gulf of Mexico. So that's why we're drilling for that in ultra deep water. So what we have a lot of is this heavy, really heavy oil. So this has about the viscosity of peanut butter. This is called bitumen. This comes from, this one's from Canada. This is the largest oil reserve on the global landscape. So this is called oil sand. So they used to call it tar sand, but it's not really appropriate. So now they've changed it to oil sands. And so this is what it looks like. And this is a mixture of sand. It's got clay, it's got water, and a semi-solid form of crude oil that's called bitumen. And this is the oil component that's extracted out of this oil sand. And so these are mined in the open pit mines up in Athabasca and Alberta, Canada, where there's currently a huge fire happening. But so this is what it looks like. And if you look in terms of the global oil reserve, this is what we want. We're running out of the light sweet crude oil that's easy to get at. So it's causing us to develop strategies to go into deeper water under the Gulf of Mexico, off the coast of Brazil. This is what we have a lot left of. So the composition and the chemistry is extremely different between a conventional light sweet crude oil, which has low sulfur, and a bitumen, which has a high sulfur content to it. So sulfur is a big deal because sulfur upon combustion forms sulfur dioxide, goes up into the atmosphere, mixes with water, and creates acid rain. So it's one of the only components of oil that is mandated by the EPA as having less than 15 parts per million, and now it's down to 10 parts per million in gasoline. So you're talking about that bitumen, that can be anywhere between 3% by weight to 10% by weight of sulfur, and you've got to get it down to 15 parts per million in gasoline. So the way you have to understand what is the sulfur composed of, what type of organic molecules is it mixed in, what is its chemical functionality, so that you can figure out how to remove it before you can make these high-value, low distillate yield products. So this is where the oil's at. So Canada is very cold. The refineries for the United States oil companies are all centered here in Houston. So you've got to get oil from here in Alberta, Canada, all the way down to Houston, and you've got a product that's got the viscosity of peanut butter. So you've got to move it through various transportation vessels. You've got to pipe it through a pipeline, and how are you going to do that with something that's got peanut butter type viscosity? I tell my kids, I'm like, suck peanut butter through a straw. You know, sometimes I let them go for a little while because they're driving me crazy, but you can do a couple things. One, you can, if anybody ever made peanut butter cookies and tried to, like, you know, your mom gives that to you to mix up, it's like really, it's tough. So you can reduce the viscosity by either heating it up, or you can mix it with water. And that's the exact same primary two components that they do for reducing bitumen viscosity to be able to transport it to do the refinery. They mix it with water, and then it's called hydrotransport. But when you mix oil with water, part of oil is soluble in water. You always hear oil and water don't mix, but that's not true. Oil does mix with water, and you get what's called these produced water samples. This one it's kind of a joke because they put it into a plastic bottle because they're engineers, and that's what engineers do. And they put this produced water into a plastic container, and plastic's made from petroleum, so all of the oil is adhered to the bottle. It's stuck to the plastic, so we can't even use this sample, and they taped it with duct tape because, again, they're engineers. So you have a problem here. What happens? What do you do with this water? You can't release it back into the environment because now it's got these toxic components, and the low molecular weight compounds are the ones that are going to be the most water soluble. The ones that are water soluble are the ones that are going to go up the food chain. So those components are the ones that are the most toxic from an environmental perspective. So in the United States, we have a different policy in terms of the oil production waste than they do in Canada. Canada has what's called a zero discharge policy, which means that anything that has come into contact or been used and is now a waste product of oil production cannot be released into the environment. Okay? So in the United States, we have different lobbying and different policymakers in the White House. So we're moving towards that type of an environmental protection stance, but we're not quite there yet. So in Canada, anything that touches water has to be contained. It cannot be released back into the environment. So they have these huge tailing ponds that are visible from space off of Fort McMurray up in Alberta, Canada, of just water, just big, huge tailing ponds are what they call them, or settling basins, where there's water that's been used in oil production but cannot be released back into the environment. In the Gulf of Mexico and in the United States, they just blow it off the side of the rig because the environmental phrase, you've probably heard it before, is dilution is the solution to pollution. So they take the water, use the water to displace the oil to get it out of the reservoir, and then the water that mixes, they just blow it off the side of the rig. Oh, wrong one. See, can't even work that. So this is what it looks like. You guys should see it. It's kind of got like a clay-like consistency to it. And so this is why you care. This is a slide that we've been showing for years. It's always a joke, and it kind of changes when the cost of gasoline is going up to $3 or $4 a gallon. Now it's down pretty low, but this is what happens. If the oil companies are spending a lot of time to make high-value distillate products like gasoline, they're not going to be the ones who take the hit on the cost. They're going to pass it along to you, the consumers. So that's why I'm never going to work this. So this is what is the big deal. Oil companies sell molecules. Petroleum is made up of molecules, over 1 million molecules per sample. Let me go back. So just can show you some of these structures here. This is just a snapshot of some of the types of compounds that are in oil. So you can have non-aromatic rings. So these are called the biomarkers or the hopanes. You can have condensed ring aromatic structures. These are very difficult to remove. You have sulfur in 2 forms. You have sulfidic or non-aromatic sulfur and thiophenic sulfur, which is in this 5-ring structure here. You have 5 and 6 ring nitrogen. We'll talk a little bit more about these as we go forward. But oil is made up of molecules, over 1 million molecules. And the type, the chemistry, the structure of those molecules is what dictates how much an oil is worth. So if you want to be able to make money off of your oil that you're getting out of the ground, you need to understand the chemistry of the compounds that are in it. Every oil is different. Every oil is unique. So you guys, everybody knows how oil is made. Oil is made from when you have biomass that degrades in the ocean, it sinks to the bottom of the ocean, and it's buried under sedimentary layers and cooked and squeezed in the Earth's crust for anywhere between 30 to 100 million years, okay? So that biological diversity, if you think about the biological diversity in Australia versus the biological diversity in Brazil versus the Gulf of Mexico versus Canada, there's an immense distribution of biodiversity, and that biodiversity is translated into the different oils that come from each region. So those of us who have been doing oil chemistry for a very long time can look at an oil and just say, oh, that's high sulfur, high nitrogen, that's from South America, or that's high sulfur, that's low oxygen, that's from Canada, or that one looks like it's a light sweet, so that must be from the deep water Gulf of Mexico area. So Ryan is the inventor of this technique called petroleomics. And so the joke was, the story goes like this: if you're doing mass spectrometry, you've got to be working under an omics umbrella, whether it's metabolomics or proteomics, or lipidomics. Everyone works under an omics, and there was not one for oil. And the director of the user program at the time and my predecessor said, well, why don't you just call it petroleomics? And she was a protein chemist, and it kind of stuck. And so petroleomics has evolved over the past decade. Here at the MagLab, this is an invention that was discovered and propagated at the Magnet Lab, where the fundamental property of petroleomics is to predict the chemical and physical properties of an oil based on its molecular composition. So what you want to be able to do if you're BP or you're ExxonMobil and you're prospecting a oil reservoir that you're thinking about producing. All right, first of all, I need to get with the seismic people to make sure how much oil is there, because I'm going to sink a $100 million well into the Gulf of Mexico. I better be getting my money back. And I better make sure that there's not going to be any of these problems that can happen due to the chemistry of the oil that I'm getting out, because then that's going to cost me money and I'm not going to make any money. So we want to be able to predict how this oil is going to behave in the refinery and how it's going to behave in oil production based on the molecular composition. And the only way that you can do that is with ultra-high resolution mass spectrometry. So there can be over 1 million molecules in a single crude, and I can say that pretty confidently, because when you've got structural isomers, I mean, we've identified 100,000 of them just by accurate mass alone, but that doesn't differentiate between structural isomers. And so we've done some statistics. There are people that have been working on this for years, that if you take just straight chain hydrocarbons and have 40 carbons, okay, just straight chain hydrocarbons, there are Avogadro's number of the way that you can put those pieces together. And that's just alkanes. That's just straight carbon bonded to each other with hydrogen saturating. And you talk about getting these types of structures and chemical functionality. You can have various alkyl chains hanging off of the sides. You have aromatics. You can have polar compounds. So these are this is a big problem. The polar components make up about less than 10% on the high end of the total weight of the compounds that are in a crude oil, but they're the ones that cause the biggest problems. So being able to identify the composition and the structure of these polar components has been a huge driving force for the ICR group for about 15 years. Sulfur, as I mentioned, is a problem. You've got to get it out before you can sell gasoline. Oxygen falls into this polar component, but also has some fun, neat tricks it plays as well. And nitrogen is a problem for upgrading because it destroys your catalysts. So just to kind of break it out a little bit, because I'm the chemist, so I'm going to show you guys a bunch of chemical structures. Otherwise, they wouldn't let me come back next year. So the cyclic sulfides, so these are about 30% of the total amount of sulfur that's in an oil is going to be non-aromatic. So these are real corrosive, so they'll eat your pipeline. So you need to be able to identify the cyclic sulfides, as well as the sulfides and disulfides. Thiols and mercaptans are another big problem. But the biggest one is these thiophene and benzothiophene, dibenzothiophene or DBTs, and you can have various aromatic and alkyl chains hanging off of all of these core structures. So my PhD work was spent trying to focus on targeted analysis of these thiophenic sulfur based on the ionization technique modifications that we do here. So I have a fond relationship with these aromatic thiophenes. So this is very difficult to remove. So if you kind of think of these are like bricks. They're not going anywhere. And if you've got 70% of your sulfur, translated that to a barrel of oil that's got 10% sulfur by weight, that's money that's being lost. So these nitrogen components in oil, they can be grouped into either acidic or non-basic, and I use air quotes when I say acidic because these aren't really acids. They don't contribute to the total acid content of the oil. And these are 5-membered ring nitrogens, and the basic components of nitrogen are these are pyridinic nitrogens, so these are very difficult to remove. If you can imagine, you can pack in a lot of aromatic rings around a nitrogen with 6 rings, and so these end up going to the coker. So these are very interesting for them to want to be able to remove them. These are the ones that foul the catalyst when they're trying to do catalytic upgrading of oils to make high-value distillate products. And the basic ones are difficult to upgrade, and they go to the coker. So that's just basically wasted money right there. So if you've got a high amount of nitrogen that's in a pyridinic form in your oil, you're not going to be able to remove it, and it's going to go straight to the coker, which is going to end up being used to pave the roads. Well, you know, you're not making any money off of paving the roads. We want to make sure that we've cooked and squeezed every last dollar before we send things to the coker. So there are some weak acids. These are a big problem, and so I'll show you some of the problems that come from these oxygen-containing. So this is a calcium naphthalene deposit. So this is formed when there is one particular type of molecule that's from an archaeobacteria. It's called an ARN acid, A-R-N. ARN because that's a Swedish word for talon, because it's got talon-like structures like an eagle talon. It's got 4 carboxylic acids on it. You think of it kind of like an EDTA soap-type mixture, and it binds with calcium and forms these soaps. Once these get into your oil production, whether it's coming into the refinery or coming out of the reservoir, the only way to remove them is through physical, manual removal with a guy in a haz-waste suit that you're obviously, you know, exposing somebody to not a lot of good chemicals and removing these calcium naphthanates. So one of the big deals about this is you want to know if you're going to have a calcium naphthanate deposit before you spend a lot of money investing it into drilling that rig.
How does he actually get it out?
With a shovel. I don't know, I think I might have a picture of it in here. But so these calcium naphthanate deposits are a big deal. They make like soap-like deposits. It's natural soaps because there's surfactants in oil just like surfactants that you use to make soap. So the guy literally has to remove it. And so this was a big deal for the Tupi oil field, which is being produced as we speak off the coast of Brazil. They were not aware that there was going to be an ARN or a calcium naphthanate deposit issue. This was discovered in the North Sea. So if you think about back when all the continents were together, Brazil was right there with all of the North Sea. So that all of that biomass that was deposited, all the archaeobacteria that were used to form, have now been separated geographically by the plate tectonics, but the same problems are there in their oil. And so you can look at the various differences between the ARN acid deposition, but they're all pretty much, it's the same problem. And so one type of compound that I'm very interested in and that I've become, it's kind of a joke, but not really a joke because I take it pretty seriously, is that these Petra Porphyrins. So I'm a porphyrin junkie. So porphyrins are the metal-containing components in oil. And so they were the first biomarkers. So up until the 1930s, Alfred Trebes is the father of modern petroleum geochemistry, and he was the first one that figured out that oil came from a biomass origin, that it had a biological origin. Up until that time, everyone thought it was mineralogical. And so he linked the structure of these petroporphyrins back to hemoglobin and chlorophyll core structures, and I'll show you those on the next slide. So this is a big problem. They concentrate in heavy oil, so oil that has a higher viscosity is going to have a lower content of petroporphyrins than these heavy ends. So that bitumen that I passed around has a very high sulfur content, so it's already problematic. It's got a high metals content because it's very young and immature, and it's got, the main type in that is the vanadium. So this is where I like to show the little Pacman slide. So if you have chlorophyll and you have hemoglobin, you've got this, they call it a tetrapyrolic. So a pyrrole is a 5-membered ring nitrogen component, and you have 4 of them. So it's a tetrapyrolic core structure, which is this circle that I'm showing right here. When it's chlorophyll, it's got magnesium chelated in the center, and when it's hemoglobin, you have iron. Now you've got biomass degradation happening over 40 to 100 million years ago, and it takes the vanadium and the nickel from the sediment around where the oil is being made. The magnesium is lost, the iron is lost, and they're transformed depending on the composition of the rock sediments into either nickel or vanadium. There are some iron that are in there, but this core structure is stable on geologic timescales. So this was the original biomarker. So you can look at the structure of these 2 main classes. They call this the cycloalkanoporphyrin. So it's got the tetrapyrolic structure, and it has 1 exocyclic ring, and it's non-aromatic on the outside. This EDO is the most basic. It just means there's no exocyclic rings after the 4 tetrapyroles. So you can look here at this structure and see that you've got these alkyl chains hanging off the side, but no other rings. So these are the 2 main structural classes, and depending on which one is in higher abundance can tell you about the maturity of the oil and the sediments for which the oil was deposited. So we used to see these compounds in oil for about 10 years and weren't exactly sure what they were. Until we were able to interrogate them a little bit further with the ultra-high resolution mass spectrometry. And based on the accurate mass measurement alone, you can determine the structure of these compounds. So this was done on the bitumen that I passed around to you guys earlier. You can calculate the number of double bonds. So double bond equivalence is the number of rings plus double bonds to carbon. So every time you make a ring or make a double bond, you lose 2 hydrogens. So if you think of benzene, that's got 3 double bonds in 1 ring, so it has a DBE of 4. And so this is an aromaticity index. So you can tell how aromatic a compound is depending on the number of double bonds, which you can calculate based on the elemental composition. So because you have bonding orders, you take the number of carbons, you divide the number of hydrogens by 2, and you add 1. And so that gives you the number of double bonds. So these double bonds are good because you can separate structural classes. So you have an EDO, which has a double bond of 17. DPEP is 18, and then if you lose 2 hydrogens, you go to 19. If you lose 6 hydrogens, you have what's called a roto-DPEP, roto-EDO, di-DPEP, and there's all sorts of structural classes because I'm not the only porphyrin junkie in the world. There's a lot of us out here. Okay. So the heavy oil deposit is enriched in these vanadial porphyrins, and so this is why you need the ultra-high resolution mass spectrometry. So this is an oil. This is the bitumen that was ran. This was ran back in about 2009. So if you look here, each one of these peaks corresponds to a unique elemental composition depending on the ionization mode that we're using. And right here, these peaks that stick up, this is a 14 Dalton spacing, and I've hit them here with a little red asterisk. And I must have ran this sample about 6 or 7 times because when you see something that's got a really narrow mass window and it's separated by 14 Dalton, you think, all right, this is some sort of a contaminant. This must be a polymer. I ran it over and over again, and I go to Ryan. He's like, oh, check that out. Let's see what this is here. These are porphyrins, and so we were pretty excited about that. And so when you take the accurate mass, these correspond to this DPEP. So this is the 1 exocyclic ring vanadyl porphyrin, and this is a 14 Dalton spacing, which 14 is the mass of CH2. So you've got a different alkyl chain length hanging off of this porphyrin core structure. And so this is why you need the ultra-high resolution, because in order to identify and separate these compounds, you have to be able to differentiate between its other compounds. They're called isobars. They have the same nominal mass but different exact mass. So the isobaric overlaps in these complex whole asphaltene and heavy oil samples have compounds that differ in mass by roughly the mass of an electron. So we're separating components by their accurate mass alone, and they differ in mass by about the mass of 1 electron. We have splits that are even smaller, but the only technique that would be able to identify these at the molecular level is ICR. So if you had a different mass spectrometer that did not have this high resolving power, you would not be able to see these 2 peaks here. You would have 1 peak. You'd assign it based on the center of mass distribution incorrectly, because you're not able to resolve and separate what's actually underneath that hump. So here's just to show you, I talked about the light sweet crude oil and the heavy sour, or the bitumen. So this just shows you the viscosity density relationship. And so here's where the Deepwater Horizon crude oil is. So this is the bitumen that you guys I've passed around. So you can see why you're going after something that's buried under 8,000 feet of water, because it's a light sweet crude oil, so it's worth a lot of money. So the challenge for petroleomics is to be able to predict these problems that can happen in oil production. So we work with a lot of chemical companies and oil companies, and whenever they have these problems that pipe up, no pun intended, in throughout the course of their production lines, they like to, I'm always looking for new pictures. So they send us these pictures. So this is a holding tank. This is a pipe going into a refinery, another pipe. So these are what some of the deposits look like. So you're talking about $500,000 if it happens over land, but if it's over the ocean, you're talking about $3 million per year. So this is a big problem, trying to understand and characterize, because of the loss of production that can result in over $1 million per day in lost revenue. So they want to be able to predict and understand how the oils are going to change in the refinery, and the same thing translates to how the oil is going to behave in the environment. So in the refinery, they call them asphaltenes. So these are oil molecules that aggregate and form deposits at various stages. And in the environment, they aggregate and float onto the beaches, and they're called tar balls or sand patties. So I'm going to pass around some of these here. So these are ones that were collected from the Deepwater Horizon. So this one, you can look at the labels, was collected from Gulf Shores, Alabama in 2011. And this one's off of the coast of Louisiana, Chandeleur Islands. It's a composite. So we work with marine geochemists that go out. I think they're still sampling over the course of the past 6 years, looking for these oil deposits. So we have oil deposits that are washed up along the Gulf beaches from 2010, when the oil was initially spilling, all the way up to the latest one we have is from October of 2015, where there's oil that is still left on the shores of the Gulf of Mexico, and we're still looking at cataloging the molecular transformations. So this is an overhead view, just to kind of show you, if you're not from this area, you might not have seen this as many times. So there was 5 million barrels of a light sweet crude oil. It was released into the Gulf of Mexico. It took 87 days to cap the rig. So this is a picture from NASA. This is taken from satellites. You can see the oil slick right here. It's about 50 miles off the shore of New Orleans, about 50 miles away from the mouth of the Mississippi Delta. So I like to show this because this is about where Tallahassee is. So the oil slick from the Gulf of Mexico covered an area about the size of South Carolina at its largest. So this is a big impact for us. The farthest east that the oil reached was Pensacola Beach, so we have quite a bit of research and publications looking at how that oil transforms. So one of our colleagues, Chris Reddy, up at Woods Hole Oceanographic Institute, likes to call them the ones that wash ashore are the toughest kids on the block. These are the molecules that have been beat up. They've not been lost to water washing. They have not been evaporated. They are still left after biodegradation to make it along the shore. So these are the ones that are going to be environmentally persistent and the most recalcitrant or resistant to change molecules. And so for us, this was not reinventing the wheel, because we had been looking at these recalcitrant compounds in oil deposits for, Ryan's been looking at them for 20 years. So we already had all of the tools in our toolkit to just take the same types of samples, these heavily weathered oil samples, and run them in the ICR to look at the molecular transformation. And so we established a molecular fingerprint of the oil that was released from the Deepwater Horizon. So this is ran on our 9.4 Tesla instrument, which you guys will see here in a little bit. So oil has a pseudo-Gaussian distribution because it's composed of biological material that's been cooked and squeezed for 50 to 100 million years. And if you take a small little slice and just blow it up and look at one nominal mass unit, so this is less than 1 Dalton window, you can see all of the different peaks that are here. Even in a light sweet crude oil, you still need to have ultra-high resolving power. Even the lightest crude oil is unable to be identified at the molecular level without this technique. And you can look here and see that this compound, this peak corresponds to 1 nitrogen and carbon and hydrogen in addition. So you have to have the right tool for the job. So you guys are going to take a walk down in a little bit and look at the scales that we use to measure the mass of molecules. So obviously there's not going to be a scale to measure at the molecular level. And so I'm not going to spend too much time on this, other than there's a lot of people in the high bay in this picture. Don't be surprised if you don't see that many when you're down here now. So Jerry Purcell works at Shell. He got his PhD under Ryan and Alan. Don Smith got his PhD doing heavy oil. He left, went to Amsterdam, went to Pacific Northwest National Lab, went back to Amsterdam, and now he's here, and his wife now works here as well. Latifah Stanford is at BP. Carol Nilsson is at University of Texas Medical Branch, and there's Ryan. Tanner Schaub's at New Mexico State. So there's quite a few changes that have been made, but the main 3 instruments that are there, you guys are going to see those in a little bit. And so why do you need this? As I mentioned, you need ultra-high mass accuracy, and you need ultra-high mass resolving power. And we're the best in the world at doing that. And so this is why you need to have the mass resolving power. It's because in oil there are 2 critical mass differences that you have to be able to resolve. One of them is 1.1 millidalton, which is the difference between an SH3 and a C13 and C4. Both have the same nominal mass but differ in exact mass. And the 3.4 millidalton, this is critical. So this is the difference between SH4 and C3. This is the bare minimum that you need to be able to achieve if you want to do accurate mass assignment for petroleum, is you have to be able to have this 3.4 millidalton overlap. As you go to higher magnetic field, you can see that the resolving power increases, but our resolving power decreases as we go out to higher mass. So this slide doesn't show the 21T, which you guys will get to see here in a little bit. So this is just one of the schematics. We build everything except the magnets in-house. So we have a very skilled instrumentation group and a machinist and a technician that design everything that you're going to see, with the exception of the superconducting magnets and maybe some electronics. So we make all of our ions at atmospheric pressure. We use differential pumping to store the ions in either one of 2 storage devices. We have a quadrupole or an octupole where we can introduce gas if we want to induce collisions to do fragmentation, or to just help prevent the ions from fragmenting using collisional cooling. They go through a transfer octupole into an ICR cell that is located in the center of a superconducting magnet. So if we zoom in here a little bit closer, this is my favorite instrument out of all of them that we have down here. This is the 9.4. So this is the same exact schematic, just now I've shown you it with a picture. And the joke is you can always tell that it's made in-house because there's tin foil and lots of wires and blinking lights. But we control everything in this instrument. Everything, we can control any parameter. There's no software other than what we build and design in-house. So we have control over every experimental parameter. If we want to measure a voltage or change a frequency, we have the ability to do that. So we make our ions at atmospheric pressure because it makes it very easy to change out samples if you don't have to break vacuum every time you want to change out a sample and clean in between. Electrospray is the primary ionization mode that we use for our user projects, and then everything else you saw there. So I'm not going to go too much into this. I know Ryan talked to you a little bit about this yesterday, or probably a lot. So we measure cyclotron frequency. We know the magnetic field. Light ions have a very high frequency, and low ions have a very low frequency. And we excite the ions to a detectable radius. So up here, I have a couple of our cells. These are old cells. These will never go back into the magnets. But I'm going to pass them around to you guys so you can look at them. So this is probably the most cookie cutter generic ICR cell. This one that I'm passing around, this one, I think we used to call it the beer can. So this has a 90-degree angle. So once you have a charge on a molecule, it's called an ion, put the ion inside of a superconducting magnet, and it's rotating at its cyclotron frequency. And it's rotating at a very low frequency, and we need to get it to a higher frequency. So we're going to apply an axial RF excitation waveform to make the ions rotate at a larger frequency. So we use 2 of these electrodes to apply the excitation and 2 of these electrodes to do our detection on. So as the ions pass beside the detection electrodes, they induce a charge. And that charge induction is then converted with a Fourier transform, and we measure that very accurately. And so this geometry is the generic one. The one that's shown over here is done, we call it the leaf cell, and then the guy who invented this and published it didn't like it, so he calls it's the dynamically harmonized ICR cell. And you can see that these electrodes, the geometry and shape of the electrodes that are used for the excitation and detection is the result of about 15 years of ion simulations and instrumentation methodology. So I'll pass these around. All of these are built in-house. And there's one that's got like loose screws on it because we use it just for demonstrations. So this is a picture I like to kind of use to remind myself of what resolving power is because, like I said, I'm a chemist. So if you look at a high field FTICR mass spectrometer like we have here at the MagLab and compare it to a photograph with the next highest resolution mass spectrometer, you can see that you get like a gray, blurry picture, and you can barely differentiate between what is actually there. If you're using high field FTICR, you can see leaf pictures, shadows, colors, everything. And that's that same thing that I mentioned to you about not being able to separate and identify them. So petroleum requires high magnetic field FTICR MS. So that's another different oil. That's from a North American oil. You establish the molecular fingerprint of the oil in its native stage. You have accurate mass assignment so that you can assign elemental compositions to everything. But this only occurs if all the ion packets maintain coherence throughout the entire detection period. So for many years, we were doing ICR, and our Russian colleague said, I don't understand how you can be doing ICR for petroleum because you've got a wide mass window. You're going from 400 all the way out to 1100 Dalton, and that means all the ions are getting excited to the same radius. So aren't they all their ion packets should be dephasing each other? And we said, well, you know, we're getting great data, and we're leading the world. And then come to find out, he was actually right. And so I'm going to go through some of that here. So you can have electric and magnetic field inhomogeneities. You can have ion neutral collisions. You can have ion cloud interactions where those ion clouds actually start to see each other. And so then that prevents you from being able to identify them. But so this was about 2010. Ryan and Chris gave back-to-back kind of bookend lectures about how petroleum requires ultra-high resolution mass spectrometry, but then ultra-high resolution mass spectrometry also requires petroleum because we do these complex mixture analysis, we were able to identify and improve the performance of ICR. Because space charge is one of the big issues that happens in ICR. If you have two ion packets and they're bumping into each other, then they're going to start to feel each other and they're going to perturb each other's cyclotron frequency. So I like to think of it, if you're standing on a scale and somebody pushes you, it changes your mass. So the ions start to see each other, and that can cause a lot of problems. And space charge is always the ultimate limiting factor for ICR, especially for these complex mixtures. And so this shows you what I was talking about. If you excite all the ions to a detectable radius and you've got ions that have a frequency range, then they're all going to start, and you put them all to the same radius, they're going to bump into each other. You've got 60 to 80,000 different mass to charge packets all rotating at cyclotron frequency. They're all jamming in together into the same radius. You're not going to be able to detect all of them because you're going to have some dephasing that's occurring. And so this was discovered. Nate Kaiser, who actually leaves us tomorrow, he's going off to Denver. He's been working with us for about 10 years now. Realized that if you excite all the ions to a constant radius across this profile, which is what in theory was thought to be the correct way to do it, to have the highest performance, then you're not going to have this ability to see a peak distribution that goes from 400 to 1200 like we need in petroleum. So what he discovered was, if you have an M/Z dependent radius distribution, so you can tune the excitation profile so that ions of different mass to charge ratios go to slightly higher but about the same radius, so from about 55 to 70% of the cell radius volume, depending on the mass to charge ratio and the frequency, then you get the best improvements made for the complex mixture analysis. So this was done by Eugene Nikolaev at the Russian Academy of Science, where he did these simulations that actually show this comet-like destruction of a small ion cloud by a larger ion cloud. So for example, if you have an ion packet at mass to charge ratio 499.5 and it contains 1 million charges, and then at 1 Dalton higher at M/Z 500, you have another ion cloud, but it only collects 100,000 charges. As these ions start to rotate with time, they start to basically collide, and the larger ion cloud destroys the smaller ion cloud. But so it gets even worse if you've got a disparity between 1 million charges and 10,000 charges, where you've got complete destruction of the ion packet coherence, because you've got a very high abundant ion cloud with 1 million versus a lower abundant ion cloud with 10,000. And remember I told you how the polar compounds are the ones that cause the most problems? Well, they're not going to be the most abundant in oil. So you need to be able to see not only the most abundant things, but the smaller abundance peaks at the same time. So this is how it translates into a mass spectrum. If you have a constant radius, so all of the ions are excited to the exact same cell radius, independent of their mass to charge ratio, and we zoom in here, this is a distribution of a distillate fraction. And you can look here and show that you got about 14 peaks above 6 times the baseline noise level. Well, that's pretty good. But now if we apply this radius distribution, take the exact same sample, you can't see that there's anything different just looking at the broadband, the full molecular weight distribution. But now if you zoom in at that same mass window with the radius distribution, the lower abundance ions are able to maintain their phase coherence to be detected at the same time as the higher abundance peaks are. So you've got a more than doubling of the number of peaks assigned just by applying a radius distribution in your excitation profile. So this, back in 2005, and Ryan's in the room, so now I'm gonna feel like a jerk. So this is the most complex mixture resolved and identified. This was published in 2005. This was world leading. So you had 11,000 peaks. You were able to resolve 25 peaks at a single nominal mass unit. 3.4 millidalton is easily resolved. Now if we take an even narrower snapshot window, you've got 55 elemental compositions within a 1 Dalton window. You have a resolving power of about 350,000, and this was the world record in 2005. Now in 2013, this is with significant improvements made in the front end of the ICR instrument, the excitation, the data acquisition, and the data assignment. This is the world record, over 85,000 peaks assigned above 6 times the baseline noise level in a single mass spectrum. 171 peaks within less than half of a Dalton window. And we're at resolving powers over 1.3 million and able to separate peaks that differ in mass by roughly or less than the mass of an electron. Across a broad molecular weight range, we have very tight mass error distribution. So this is mass to charge ratio versus mass measurement accuracy. And what you want to see is that everything is centered around 0. And so we have an RMS error of less than 130 parts per billion across that entire distribution. So this was also the result of getting new samples in. So we started to get users that had samples that had been heavily weathered, that came from various places around the Gulf of Mexico. And then they remembered, oh, I've got these tar balls from California that I've been working on for 20 years. Would you like to take a look at them? So as we started to have an influx of users coming from the environmental, they brought us new, more challenging, exciting samples. So the Deepwater Horizon blowout happened in 2010. So this is the number of peaks assigned since the first petroleum spectrum was collected on an ICR instrument. And you can see that it gradually increases until about 2010 is when we started to get these really heavily weathered oils. So these are all weathered oil samples, but this is a combination of modifications to the instrument and the excitation profiles of the cell geometry. So this was a refinery residue. So this had been exposed to temperatures above 600 degrees C that was collected in 2010. It was about 37,000 peaks. These are all weathered oil samples that have been collected since then. But the joke is, I like to say that I joined in 2005, so that's why we've been on an upward slope ever since.
So why did it take so long to be on slope?
Hey, I'm a chemist. I'm slow, you know. I'm a little slow. I need to have it explained to me slowly. So this is a non-distillable fraction. This just shows you how bad it can get. So you have almost 250 peaks across about a 500 millidalton window, and every single one of these peaks corresponds to unique elemental composition. So this all has to be done at a very finite window. So compositional comparison between what Mother Nature can do and what a refinery can do, or what big oil can expose it to with high temperatures. So this is that residue from a vacuum distillation tower. So this has 37,000 peaks in it, been up to 600 degrees Celsius, so that's really high temperature. But if you look at a tar ball that was collected, this is less than a year after the oil spill erupted. That was April 22nd in 2010. This was from Gulf Shores, Louisiana, Gulf Shores, Alabama. There's 60,000 peaks, and this has only been exposed to environmental conditions. So environmental temperatures, environmental pressure. So it hasn't been heavily cracked or put up to 600 degrees, and you can see that it's got a more than doubling of the number of peaks that you had from a refinery residue, very complex, 80 peaks at a 1 Dalton window, and it's because Mother Nature is the best organic chemist. This oil has been exposed to numerous abiotic and biotic processes. So you've had adsorption, some of it's emulsified. You have photooxidation happening to the oil that floats on the surface, evaporation, dissolution, dispersion. And the Gulf of Mexico is heavily biodegrading because there are a lot of natural seeps in the Gulf of Mexico already. So there are microbes and microorganisms that get their carbon source from oil that is released there naturally. And now you just fed them filet mignon. You gave them a light sweet crude oil. So the microbes have gone crazy on this oil already. So if you look just at the bulk elemental analysis of the whole crude oil and a tar ball, you see you've got a huge increase in the oxygen. This is a problem for every other technique, because what happens when you have something that gets more highly oxidized is it starts to become more polar, so its volatility decreases. So now you've not only decreased its volatility, you've pushed it outside of the analytical window of the technique that is most used to study oil, which is gas chromatography. So as these things become more oxygen enriched, their volatility decreases, and the only way that you can address them at the molecular level is with our technique. So I showed you this a little bit earlier. This is the wellhead, this is a surface slick, sand patty, and a rock scraping. And if you just look at the bulk, you can see that this wellhead oil has this polar fraction. This is a peak from a thin layer chromatography. It starts to increase as you go to these heavily weathered oils. So when you start looking at things that have been exposed to the environment and that are sitting in either the sand patties on the beaches or the rock scrapings, the only techniques that are going to be able to address that high oxygen is what we have here at the Magnet Lab. So I'll just show you last couple slices of this here, literally. Pensacola Beach is the farthest east the oil ever went. It hit in 2010, June 23rd. So this is a big deal because Pensacola gets its money from tourists coming down to see the white sandy beaches. And so a lot of decisions that were made on the fly by the Army Corps of Engineers and the Coast Guard when the oil spill happened were made snap decisions to protect these white sandy beaches, because nobody wants to see black oil floating in on the white sandy beaches of Florida and Alabama. So there were a lot of things that drove the decision. They used chemical dispersant at the reservoir for the very first time without really having much information to know how the long-term effects were going to be. They just wanted to prevent CNN camera crews from being able to show oil waves washing ashore. So when the oil did hit, they had crews of people that would come out and clean the beaches off with shovels and then dump new sand on top of it. So whether or not the oil had percolated down into various depths or there had been oil replenishing happening depending on each of the different municipalities, oil is still there. So we had an oceanographer that works with us at Florida State University. He was able to get a permit to take a backhoe out onto Pensacola Beach and dig down into the sand. And so that's what we're showing right here is one of the scoops. And you look this is about 50 centimeters, and he's got a Sharpie here for scale, and you can see you've got almost like this bathtub ring effect happening. Well, what we wanted to know was, does the oil composition change as you go down in depth? So he took it in cores, just like they do the ice cores, and sectioned them at various depths, because he works very tightly with a microbiologist at Georgia Tech who is interested in studying the chemical composition and the impact on the microbial community, because at different depths you've got different ecosystems that are living in the microbe world. So we had these jars, we still have them frozen. We did an extraction and we looked at the compositional difference that happens between the oil at the surface and the oil that leaches all the way down into the bottom. And so just to kind of show you how this complexity changes, this is the pre-spill Deepwater Horizon oil. This is before it was released into the environment. You had about 28,000 peaks. Now if you look at the comparison between a Gulf Shores, Alabama sample, you see a couple of things have changed. One, the most abundant peaks in this wellhead crude oil are about at a mass to charge ratio of 3 to 400, and they're almost completely removed in the Gulf Shores, Alabama sample, which the molecular weight distribution shifts to higher molecular weight at about 650 or 700, and you've got a twofold increase in the number of peaks. So you want to be able to understand what's going on here at the molecular level. So this is the last slide. Renee, don't yell at me. I know you want to go see Ferris Bueller. Okay, so this is the Deepwater Horizon crude oil, and just to kind of show you what I was talking about, the polar components, all of the most abundant peaks across the same mass range in the Deepwater Horizon crude oil contain one or fewer heteroatoms. So anything that's not carbon and hydrogen is called a heteroatom, nitrogen, oxygen, sulfur. So here, hydrocarbon, that contains 2 sulfur, but it's very low and abundant, 1 oxygen and another hydrocarbon. But now if you look at that same mass window for the tarball, every single peak contains at least 2 oxygens, so it's becoming more polar because it's heavily biodegraded, so it's becoming less volatile. So the only techniques that can access that are with electrospray ionization and with our ultra-high resolution mass spectrometers. And that's it. That's all I have for you guys. You can come up. I've got more samples here. I'm happy to answer any questions that you guys might have. Thanks.